so I serve mostly as the research advisor for conducting our research to discover a solution, and also in hardware design for development or theoretical development of our EEG model. So we want to show the real impact that concussions have, not only on the athlete populations, but in the United States as a whole. So there are about 2.87 million TBI-related ED visits in the US annually. And that ultimately comes to 5.3 million Americans living with TBI-related disabilities throughout that year, throughout the rest of their lives. It's a very pervasive problem in all areas of sports, as there are about 3.8 million sports-related concussions occurring every year, with demographics as such occurring, where in basketball, football, and particularly wrestling, there's a very high prevalence of concussions relative to the number of people who play the sport. In this way, concussions hardly receive the necessary attention in several of these fields. There have been great strides made in the realm of football, such as the NFL or high school football, towards addressing concussions, but there's still a lot more to go in that field. Particularly in other sports, there's a very unmet need for concussion diagnosis and concussion recognition among athletes. And among athletes, there's a 10 times higher risk of second impact syndrome after the initial concussion. This indicates that upon a secondary impact while dealing with concussion, this causes much more severely altered mental status and sometimes permanent brain damage. And the long-term effect of this permanent brain damage can be extremely detrimental in changing the ways in which chronic MTBI patients interact with the world. The reason that I hopped on this project was because I had an experience where a friend up in school suffered a concussion due to an accident, but they were not properly diagnosed after the fact and were living with the concussion for a while. So then after about a month, they suffered another hit that caused them to have a repetition of concussion. And after that concussion, their mental status was noticeably altered. They seemed a bit more spaced out than normal. They were a little more difficult to engage with and solidify plans with. And at worst, it even resulted in some scenarios of paranoia, anxiety, and instances where they're not able to sleep as well. So I've seen the real impact that undiagnosed concussions can have on altering the livelihood and the condition of people, just regular, ordinary people and athletes alike. So I really want to help mitigate this issue and make sure that we can have early diagnosis and detection so that we can fast track that treatment process.
Yeah, and like piggybacking off of that, like I'm just generally interested in neuroscience and mental health research. That's kind of where I want to go in the future. And I found that actually was a great way to get involved with preventing mental health like issues before they occur. Specifically what Will was talking about, how I was trying to just slowly change. And that's a really serious issue, especially again like the pressure to keep doing whatever you're doing, you know, you're young,
order to tackle this solution, we decided on a three-pronged approach in order to address it for multiple areas. First and foremost, we have a real-time concussion risk detection system through the form of a web-based concussion assessment that combines symptom checklists with auditory reaction tests. This test is modeled after SCAT-5, which is a traditional concussion assessment test, in addition to all protocols, which encompass the demonstration of expected and repeated patterns towards a patient, and then suddenly changing that pattern with a deviant either auditory stimulus or visual stimulus in order to observe the way that their electrical brain activity reacts in response to that sudden change. This model captures the subjective and objective cognitive data through their selection of the assessment as well as their reaction times and stuff like that. And it results in a fast, accessible, and a user-friendly approach to assessing their concussion risk for athletes and clinicians alike. Second off, we have an integrated helmet EEG system. This system is able to accurately track brain data during continuous activity and provide continuous data streams of their brain's electrical activity to a cloud platform. This captures both biomechanical and neurological data in a single device. It enables a scalable, real-time concussion monitoring system so we can track alterations in brain activity in real time. And as I mentioned, this data would be transmitted to a cloud data set, which provides proprietary data sets to fuel future AI development. And in addition to this, we would ensure that our helmet system would be compliant with National Operating Committee on standards for athletic equipment, so that this helmet would be able to be utilized in sports such as the NFL, football, stuff like that, and be able to use in compliance with current safety standards. And lastly, we are developing an AI model for data interpretation that will be able to successfully interpret EEG data and produce an informed diagnosis as to a patient's concussion risk. This automates the diagnosis process to alleviate the clinical burden on clinicians and trainers, and enhances accuracy of concussion diagnosis through pattern recognition at large scales. And this will enable real-time decision support making and long-term tracking of patient concussion health. So in order to demonstrate a proposed impact, we developed a hypothetical scenario with Coach Daniels over here. Coach Daniels is a 45-year-old high school football coach leading one of the top-ranked teams football teams in a small sports-focused town. His needs are that he needs to keep his athletes safe without sacrificing his team's success, as they're very widely ranked or highly ranked. He needs to be able to make confident, timely return to play decisions so that he can keep his players healthy and keep his lineup strong so that they can compete at a very high level. He also wants to be able to avoid liability and avoid detriments to long-term athlete health by keeping his athletes healthy in the long term, preventing chronic MTBI conditions. He is able to keep his players on the field and keep a strong program. However, the pain points of his program is that he lacks often objective tools for concussion detection and difficulty with technology access, because I'm sure y'all I remember in high school, a lot of concussion assessment broadly revolves around a single test that's taken by all athletes and then reflected back upon in the instance of a potential impact. But this system is often ineffective for detecting concussions in real time. A statistic that popped up earlier was that 50% of concussions often go undiagnosed. So this has proven that that system for detecting concussions is very effective, and it needs to be innovated upon in order to provide real, applicable ways to measure concussion risk in these athletes. He often struggles to keep players on the field when they seem concussed and deny their symptoms. This is a large personal impact where these players want to keep playing, but because there aren't systems in place to be able to realistically tell them their concussion risk after an impact, they are able to deny their symptoms, deny their true health status, and continue playing and put them at higher risk of further second impacts. And lastly, he feels pressure to keep star athletes on the field due to the community and team standards that are expected within this community and expectations to perform. How Mindshield could help this is providing Coach Daniels with fast, science-backed tools that will be able to assess concussion risk of his players and empower him to make informed decisions of how to provide treatment to his players when they suffer a potential impact, and be able to protect them in the long term so that a successful program can keep his kids healthy. So now we're going to dive a little bit deeper into the different approaches that we're undergoing. So first off, our hardware. So our theoretical helmet design involves dry EEG electrodes. These electrodes make direct contact with the scalp without involving conductive gel. Oftentimes, when you have an EEG applied in a clinical setting, they use conductive gel in order to provide a better connection between the brain and the electrodes, because the skin between the skull and the skin provide a rather high impedance barrier between the electrical activity of the brain and then the electrodes, so it becomes difficult to measure electrical activity without conductive gel. However, dry electrode technology has emerged in recent years as an alternative that is much more scalable and cost-effective than blunt electrodes, because not only are they more hygienic for multi-patient use, but they also have pre-built-in amplifiers that are able to enhance that signal to eliminate noise of the system and overcome that impedance barrier that the skull and skin provide. And this brings me to my second point about active electrodes. Active electrodes are the technology that enables these dry EEG electrodes to work, as these pre-built-in amplifiers allow the EEG signals, specific brain waves, to be amplified in such a way that we can target specific signals within the brain and shield out all other undesired signals. So not only would these two combinations, or not only would this combination of electrodes provide us with a scalable cheap solution, providing EEG hardware in a broad sense, but would also enable us to have a very easy to apply solution and easy to integrate product that would be scalable with athletes of many different sports and be much easier to utilize essentially by trainers. Another thing we have to consider is an adjustable electrode setup, because we are trying to integrate a EEG hardware setup within a helmet. We would need to have it adjustable to different shapes and sizes of athletes' heads, so that we are going to, similar to this image, have adjustable bands that would be able to alter the position of electrodes and alter the size of the internal shell of the helmet, so that we can ensure a comfortable and effective fit with athletes. And lastly, we would integrate a data collection system into the helmet that would be able to transmit collected data through the EEG hardware to an external platform through local network connection. And this is just an example of the type of hardware we would use. This is not our own design. Credit goes to Zito Incorporated, who have designed this dry EEG electrode system that is able to that applies these dry EEG electrodes and active electrodes that I discussed before in order to simplify the EEG collection process, and they serve as a potential collaborator for future work. Next up is our research. So in order to fully quantify, in order to fully assess concussion risk, we needed to identify specific biomarkers within EEG assessments that would serve as potential indicators of concussion risk. And through the research that we conducted, there were several event-related potential studies. Event-related potential is electrical activity in response to a certain stimuli. So visual stimuli, auditory stimuli, that result in change in electrical activity is reported in ERP studies. And those studies consistently find that there are diminished responses of the P3A and P3B subcomponents of the P300 ERP, and that can correlate with history of mild traumatic brain injuries. The P300 signal is a specific signal that's found in the frontal lobe and then primarily in the parietal lobes of the brain. And this signal is very sensitive to attention and awareness to surroundings, to the cognitive response to stimuli, and to decision making in response to those stimuli. And these two subcomponents are very important because the P3A subcomponent is associated with the shift in attention in response to a deviant or oddball stimuli, and that P3B is related to the processing and storing of that stimuli and the integration into working memory, so that the patient can then act on that stimulus. In experience involving this type of oddball stimuli, patients are subjected to a sequence of sounds or images that are fairly similar to each other, and then once they're used to it, a variant is introduced, and their brain's electrical activity is reported in response to that deviant. And then frequently in MTBI patients, the P3A and P3B responses diminish. So in order to further study this, we identified a data set that was in existence titled Free Stim Auditory Oddball in Breast in Acute and Chronic MTBI. And in this study, participants were presented with a sequence of frequent standard auditory stimuli interspersed with infrequent deviant stimuli. And through this, the P300 response, along with the P3A and P3B subcomponents, can be isolated through the filtering of data and selection of specific channels through the study. So what we did is we compiled the data into MATLAB, specifically a toolkit called EEG-Lab, and filtered the data through a bandpass filter between 1 and 30 hertz, rejected false data, and then recorded which effects were specifically relevant to these oddball stimuli. And then once we isolated that data and filtered and processed it, we then isolated these 3 electrodes along the scalp. This is the FZ electrode, which corresponds with the frontal lobe, the CZ electrode, which is on the border between the frontal and parietal lobes, and then the PZ electrode, which is the parietal lobe. By isolating these electrodes, we then plotted the ERP channel plot waveform in order to identify what these signals look like, how their brain was responding to these oddball stimuli. So then we plotted this image. In this image, the P3A curve corresponds with the blue curve, and the P3B signal corresponds with the orange curve. So P3B is found typically in the PZ, and P3A is found typically in the FC. So then we encompass these different regions and plot the waveform over time to observe the potential, the latency, and whether there are multiple fragmented peaks. And what we hypothesized is that patients with MTBI would display lower amplitude, so a lower range of potential. They would display higher latency, so the expected range of this P300 signal, specifically these 2 subcomponents, is between 300 milliseconds and 600 milliseconds. The P3A typically occurs earlier, and the P3B occurs slightly later. So then our hypothesis was that in MTBI patients, that the P3B signal and P3A signal will occur later than 300 milliseconds and 600 milliseconds. And then lastly, we hypothesized that there would be more fragmented peaks within MTBI patients that would correspond with poor synchronization between different regions of the brain. And as hypothesized, we found that MTBI patients had delayed latency, reduced amplitude, and fragmented peaks.
And then you just visually see that like comparison with this is like asymptomatic with no concussion detected. Just visually looking at the graph, so they're very different. Just in plain terms.
Yeah, as Will mentioned, here are our results. So here are some examples of control patients. And as you can tell, the potential range of some of these patients, I can't put those numbers on that image, but I believe that it scales up to, on this image, up to about 4 microvolts, and up here to 6 microvolts. And we see that the peak for the P3A amplitude for these patients tend to be about here, right around the 300 signal is where their P3B signal is occurring. For that patient right there, you can see the resulting activity on the scalp map. But then with these concussion patients, their amplitude for the P3A or the P3B signal is much lower. So right about here is where we expect the P3B signal to be for this concussion patient. But as you can see, it's about 1 microvolt, which is significantly less than it was for these patients, where for this one it was about 4, for this one it was about 3. So there's a diminished response in amplitude. In addition to this, there's multiple fragmented peaks in this patient's curve that constantly dips up and below the x-axis and has multiple small stimuli, and that indicates disrupted neural synchronization and poor cognitive response to the stimuli. And lastly, which is very evident in this one, is delayed latency. So you can see higher signals associated with P3B response occurring much later in the trial than expected. So through this, we can identify that the lower amplitude corresponds with reduced cognitive engagement and difficulty in processing that oddball target stimuli and reconciling that difference in stimuli. And then the delayed latency demonstrates slower processing and difficulty coming to grips with what the new stimuli was, breaking that pattern. And as I just mentioned, fragmented peaks are correlated with disrupted neural synchronization. So what these results tell us is that P3A and P3B signals are promising biomarkers for concussion risk, as they demonstrate quantifiable differences in electrical activity in response to oddball stimuli. And this also indicates to us that we can tailor our hardware design around these 3 electrodes as Since the signal is strongest in this region, we are able to design our hardware around focusing on those specific electrodes, which will allow us to cut costs and ignore the introduction of electrodes that would be where data provide noise. And through this, we hope to do further research in the future that would prove the efficacy of these biomarkers further and promote the detection of signal deviations in order to train an ag model. And I think that's to add on this one.
Based on our competitive analysis, it's clear that